we will also use in this lecture on maximum flow, we will use a sub-algorithm that is called depth first search on graph. So some of you may already be very familiar with this algorithm, but I will remind you some important concepts and how it works and the time complexity as well. So it's an algorithm that is used for traversing a graph data structure. We start at the root, and the goal is to visit every node if possible. And once we have visited some nodes and we reach some dead end, we will have a backtracking. And so during the execution of the algorithm, we will partition the nodes in 3 different color types. There will be the white color nodes are the nodes that are not yet visited. The gray color nodes are the nodes that are open, if you want. That is, we are currently visiting them, but we still have to visit some of its adjacent edges that are not yet visited. And the black edges, it means that we are backtracking from them, okay? All its adjacent edges have already been processed. Let's see an example. So initially everything is white. We will start from that one, from the node number 4. Okay. Then we visit, sorry, we start in 1. Okay. So that one will become gray. Okay. Then we visit the 3. It becomes gray as well. And then we visit all its successors. So that will be 2. It becomes gray. And you see that we are done for number 2. So it becomes black. From number 3 as well, we have nothing else to visit aside from 2, but it's already done. So that one, when we will backtrack, we will arrive here. It become black as well. And then there is still another one that we can start because it's still white. That's the number 4. Yes, we backtrack first from that one. Okay, and then we have to visit the number 4. It becomes gray. We return from it, and that's it. And so at the end, if you look at the parent state of where you are coming from when you have visited the nodes, this is what you have. You have this, and we call that a forest. Okay, a forest that is composed of trees. You have one tree here, and you have one tree here, composed of this single node. So the parent vector, that is where you are coming from, encode the forest. It will encode the forest. Each node of the graph is part of the forest, and an edge VU is part of the forest if the node V was visited during the processing of edge UV. And then U is called the parent of V is in that case. And we will represent the forest using an array representation like this. The parent of node V is equal to U, okay, and that will encode the forest. Okay? Because you can, in a forest, you can only have one parent node. And so this is why we can implement it with an array representation. Let's study the source code of this depth first search. So initially, we will create global variables for the color and also for the parent that will encode the forest, if you remember. Then for every node, we initialize its color to white, and the parent is null initially. And we will start the search for every node that is not yet set to color white, and we visit it. The first thing that we do when we visit it is that we color this node in gray, and we will try recursively to visit all its adjacent edges. So for every node adjacent to node U, the one that you just called here in argument to visit, if its color is still white, you say that you are coming in this node from node U. Okay, and this is why you encode here. And so you will add an edge to the forest. And then you recursively visit that node V that you just discovered. And then when you come back and you have recursively visited and you are done by recursively visiting all the adjacent nodes that are not yet set, that are still white, then you set the color node of U in black. And so the time complexity of this algorithm is order of number of nodes plus number of edges, right? Because here, initially, for the initialization here, initialization will be order of V. But then you will visit every edge, right? Because of this, you will visit every node once and every edge once. And therefore, the time complexity is order V plus E. So that's depth first search. So it's really an algorithm that is used for visiting the edges, but it's also as a byproduct, you have this very interesting data structure that is also created for you, which encode the forest. Okay, the parent data structure encode the forest, and you can use this data structure to find a path in a directed graph. So if you want to discover if there is a path in a directed graph, you will just adapt depth first search. Instead of calling visit on every node, you just call it on the origin node, okay? The origin node, because you are interested to find a path from S to T, so you just start it. Instead of calling it on every node here, you will just visit, you will just start it from S, right? So you start from S, and then you can retrieve the path by visiting node T, the parent of T, the parent of the parent of T, and so on until you come back to S. And that will be the path in the reverse direction from T to S. And then you can just reverse it if you want to recover it from S to T. On the other side, if you realize that the parent of T is still null, then you are sure that there is no path from S to T. So depth first search is also used to find a path from a node to another node in linear time in a directed graph. It doesn't mean that it is the shortest path, okay, but it is a path. And that you have the guarantee that if that path exists, if at least one path exists, you will find at least one path. And if it does not exist, you will have the case that the parent of T is equal to null at the end. So if you are interested to find a path from 4 to 3, for instance, okay, you start like this, then you start from 4, then you visit 1, then you visit 3, then you visit 2, 2 becomes black, you come back, then 3 becomes black, and you return from there, right? 1 becomes black, and so your forest at the end is this one, okay? Your forest is this one, and so this is exactly the link here that you see are exactly the parent data structure that you just have at the end of the execution of depth first search, and you can retrieve the path like this. Okay, you can retrieve the path, and so you would start from 3, and so the path that you will find, if you put it in the correct direction, is that one. Okay, and as you can see, it's not the shortest path, right? Because this path was shorter. You could have reached 4 and then 3 directly, but instead, what you discover with the depth first search is 4, 1, 3. Okay, that's one step longer, but it's a path, and as I said, if there is at least one path, you will find it. So this algorithm finds a path from the origin to every other node reachable from S, and not only toward the destination T, okay, because you have a forest at the end. And the representation of all these paths is encoded with space complexity of the order of the number of nodes. That's the size of the vector parent. That's all I wanted to say to recall a little bit the depth first search that we will use a lot during the maximum flow algorithms.